Thanks again for the invitation. It's really a great honor to be here. This talk is going to be about my experience working on distributed machine learning, in particular ways to scale the training of deep neural networks. This talk is based on my experience as an academic or as a researcher working at IST, but also working as like an ML research engineer, and now sort of the ML research lead at Neural Magic, which is a startup based in Boston, Massachusetts. I'll try to sort of take you through really the basics of this area, which is a fairly new direction for distributed computing, but also at the same time show you a bit of the sort of the like nitty gritty, the sort of the bad, and also like the really nasty stuff, which is kind of what mean to tune hyperparameters and so on. So without further ado, I'll maybe start, and I'll start with a broad introduction into the area. So basically, my guess is most of you must have heard of machine learning as a buzzword, and of deep learning as kind of one specific area of machine learning which has made a tremendous amount of progress recently. So this is kind of a very hyped area. So what are really the facts? The facts is that there are these machine learning models, in particular neural networks, in particular deep neural networks, which are able to match or surpass even sort of human level performance at some very narrow tasks in computer vision, like image classification or image segmentation. So image segmentation is basically recognizing objects within an image. And then also at speech recognition and translation, transcription, and so on and so forth. So there's basically papers claiming basically matching human accuracy or even surpassing it on some of these very specific tasks. And then maybe the third and perhaps the most sort of spectacular application of these models has been in the context of strategic games. In particular, my guess is most of you might have heard of AlphaGo, which was able to beat sort of one of the top players, or some of the top players in Go, which was believed to be close to impossible, or at least very, very far away in terms of feasibility, right? So as I said, these tasks are fairly narrow, and this area is kind of overhyped. So it's a really reasonable question, it's sort of a reasonable position to be kind of skeptical or maybe ambivalent about the area. So in my experience, this is why I sort of stress the fact that these tasks are narrow. I don't think we're that close to having artificial general intelligence. However, in terms of industry adoption, one thing that I really noticed in the past couple of years, and due to my involvement with Neural Magic, is that these tools have gained very wide adoption industrially. So basically, even if there's no more research paper on learning published starting tomorrow, the amount of progress which has been done over the past decade is important enough that existing technology will permeate industry. So I think it is important to learn about how to sort of work with these tools and how to deploy them. And this is maybe the main motivation for my choosing of this topic. Okay. So and it's also reasonable to ask what are the key factors which have enabled this recent progress. I mean, it's very rare that within a decade, there's so much progress in terms of accuracy or applications for an area of computer science. In my view, the first and foremost is basically the great ideas which went into kind of designing these models, finding methods to train them, finding new applications, and so on. And it's only fitting that some of the three of the seminal researchers in this area, in particular, Joshua Bengio, Jeffrey Hinton, and Jan LeCun have won the Turing Award last year for their contributions to deep learning. And then the second key aspect of this is that these models, they're notoriously data hungry. So the more data you sort of you throw at them, the more accurate they get. So they need a lot of labeled data, basically images labeled with the objects within them, or speech data labeled with transcription, and so on and so forth. So basically, this has been made available by very wide communities of volunteers. In particular, I mentioned here ImageNet, which is this database of about 20 million images and counting, and then speech data, which has been prepared by NIST or other organizations. Okay, so great ideas, high quality data, but also crucially efficient, the ability to do efficient computation. So I checked briefly before the talk, and very roughly it seems like the computational speed of a single node, which computes matrix multiplied as applied to machine learning applications, which is kind of one of the key things that these models are running over and over again, has increased between 100 and 1,000-fold in the past decade. So we have sort of Moore's law, but notice that with respect to this specific area, the amount of sort of computational speed up has been really amazing, and this really enables us to run larger models and try out larger applications and so on. So this is, I do believe this is a crucial component. And as you can see, this is now supported by all of the main cloud providers like AWS, Google Cloud, or Azure. So in particular, the one aspect which my talk focuses on is clearly distributed and parallel computing, which I believe is kind of the key enabler of computational speedups, and it's the key enabler and practice of this area, because at the beginning of the 2010s, it would take you weeks, months, or even years to train a very large model. So the iteration times were enormous. You just imagine having to do your PhD in this, where you would have to wait half a year for an experiment to finish. So the fact that distribution has enabled faster iteration times has really been one of the key enablers. And this is the topic that I want to focus on today. So distribution is key, since this is the Hydra is a sort of distributed concurrent programming conference. I guess I don't need to motivate that too much, but I can explain what it is about in the context of neural network training. Okay, in particular, the main computationally heavy task that we care about in this context is training deep neural networks efficiently. On the right-hand side, you have like one instance of a neural network. So this is basically sort of blocks of matrices which you need to sort of compute over in order to obtain a result. So the key thing that sort of strikes you as you kind of have to train a network is the size of the data sets on which you need to train. So for instance, the ImageNet 1000, sort of a subset, sort of the main subset of the ImageNet data set I mentioned earlier, has about 1.3, 1.5 million images. And basically, in order to train a model, you have to go over this million images about 100 times. So in particular, you have to see, this is a tremendous number of samples that you have to go over. And the new generation of data sets, for instance, open images from Google, is one order of magnitude over this size. And for speech data sets, this is in the order of thousands, if not hundreds, tens of thousands or hundreds of thousands of recorded hours of speech. So this already sort of matches the amount of speech data that, let's say, a human child would hear until the point where they start speaking, right? So I'll give you an example of sort of a proprietary speech data set that we work with from Microsoft towards the end of the talk. So the point of talking about size is that currently, even with the most expensive sort of GPUs or like computational devices out there, these number of samples are just way too large for a single compute node, like a single GPU or CPU or a TPU to compute over. So basically, in order to train these models, you have to split the samples and sort of process them in parallel. So distributed training is necessary. There's no way to go around this given this data set size. Okay. Now, on the other hand, the thing that sort of generates conflict here is that the models, which is basically all of these sets of parameters sort of stacked on top of each other, they're also very large. So kind of state-of-the-art networks are in the order of tens, if not hundreds of millions or even billions of parameters. And all of these parameters, they have to stay in sync across all of the computational nodes in order for the computation to sort of still make sense and for the model to converge to a properly trained. Okay, so the idea is that, I mean, the conflict here is between the fact that we want to distribute training among as many nodes as possible in order to reduce end-to-end training time, and the fact that models have a lot of parameters that need to be synchronized every couple of milliseconds. So basically, there's a conflict between communication and synchronization and the number of nodes that we need to split over. Okay, and all of the current frameworks like TensorFlow or PyTorch and so on, they try to address this somehow, and they do propose working solutions for this. So a reasonable question, given the amount of interest that went into this, is distributed machine learning kind of a solved problem? And I'd like to argue that it's not. So for this, I'll give you a small example. This is an experiment I ran at some point last year. So things might have changed slightly, but I think the point of it is still valid. So we have access to CSCS BizDaint, which is Europe's top supercomputer. It used to be, I think, world third, and now I believe it's world fourth in terms of total computational power. This has about 4,000 GPU nodes connected by a state-of-the-art network, basically one of the best computer networks that money can buy. So this is kind of above the grade of sort of cloud grade computer network. And the task that I try to use this supercomputer for is training a ResNet model on the ImageNet dataset, which I just mentioned before. So some of the parameters you can remember from the previous slide. So if I trained this model on a single GPU node from CSCS, it would take me about 19 to 20 days. This is kind of using the up-to-date version of TensorFlow at that point. And if I was able to perfectly scale this training process across just 1/4 of the number of GPUs that CSCS has, then it would, in theory, it should take me about 25 minutes. So that should be a pretty good sort of bang for the buck scalability scenario. Okay, so let's see what happens with this in practice. Okay, so on the x-axis here, I have the number of GPU nodes over which I train. And on the y-axis, I have the number of days the training process would take. So just imagine that I have this bar here with 19 days on one node. And then if I ran on two nodes, it would take me about 9.6 days, which is a pretty good kind of scalability scenario. Notice I'm just losing 0.1 days. However, that 9.6 days is still a very long time to wait for just one iteration of your training process, right? One kind of end-to-end training. Now, if I go to 4, it's 5 days, so it's still okay in terms of scalability, but not in terms of time. And then if I go to 8, it's about 3.2 days. So again, it goes down. That's good, but I'm starting to suffer because of poor scaling. At 16, it's 2.4 days. But then at 32, unfortunately, my time actually starts to increase. So notice that I'm using more nodes. I'm splitting the work per node is smaller. However, the total end-to-end time increases. And then 64 is 3.1 days, which is getting embarrassing because basically I'm using more nodes, like 8 times more nodes, but it sort of takes me pretty much the same time as 8 nodes. Okay, so I mean, for those, most of you can kind of guess why this happens, but let's try to sort of dig deeper into this. So basically, what we can do is we can sort of split this time, which is deployed, sort of shown per node. We can split it into computation time and communication time. Okay, so notice that computation time should always halve, like be divided by 2 every time I double the number of nodes, because there's just less work per node to perform. Okay, we just have twice the number of nodes, so we can split the work. However, what happens is that we are seeing an increased impact of the communication time as we increase the number of nodes. So notice that communication time initially is kind of negligible, but then at 64 nodes, we're in the very embarrassing situation if you're into kind of distributed computing, where you have like 90% of your time going into communication and synchronization. So this is basically just overhead, and only 10% of the execution time which goes into computation. So that's pretty bad. I mean, this is something we should be able to improve upon. And towards the end of the talk, I'll show you some actual numbers of some stuff that we can get in this context. So my point here is really not to bash like the people of CSCS, which actually maintain like a super nice machine, or to sort of say that TensorFlow is sort of a bad framework. It's not. It's actually very well designed and engineered and implemented. But my point is, in this particular example, is that efficient distribution is still non-trivial. So this is not. It's not something where you just turn a key or press a button and it just works. Okay. So this is kind of a long motivation for the rest of my talk. Okay. So in order to understand what like sort of how to improve this, we first need to understand what the algorithm looks like. And the algorithm basically at a high level, it looks as follows. So we have all of these computational nodes, in this case, 4 nodes, and they share, each one of them has a slice of the data set, which I'll just sort of describe using this kind of uh, like blue thing over here. And then they perform the following kind of computational path for many times. So basically, they sample some data from each from their local data set, and then they compute an update to their model, which would reduce the loss of this model on the data. And then they have to average their updates in a kind of all-to-all fashion in order for all of them to sort of have each other's updates. And then they update their local model. Okay, so this is, I mean, logically, sort of, hopefully it makes sense. And then they just repeat this pattern for hundreds of thousands, if not millions of times, just like taking a sample, processing it, updating, and so on and so forth. You do this kind of forever and ever, and you end up with a model which can sort of tell about cats from dogs or something. Okay, so this is kind of the basic intuition. Like, what happens if we increase the size of the model? So basically, if we increase the size of the model, this kind of computational part increases because we have to compute updates for more parameters. So that sort of makes sense. However, what's kind of annoying here is that also this update averaging part also increases. So this happens because sort of this kind of synchronization communication time is proportional to 2 factors. It's proportional in the size of the system, how many nodes you have, but also in the size of the model. Okay, so if you try to scale up, as I showed you before on a large model, this part will tend to grow faster than this compute part. Okay, and the model update part is kind of proportional to the size of the model, but it's not very meaningful in practice. Okay, so what happens in the case of parallel HDD on really large models and maybe large number of nodes is that you have a large amount of compute, but also your synchronization, sort of the update averaging part, can grow to sort of overcome the compute part, which is kind of why we saw that this only takes about 10% and this takes about 80% in the particular example I showed you before. Okay, so all right, so what is today's talk about? Today's talk is about removing this roadblock and seeing how we can reduce the impact of communication and synchronization onto these types of systems. So it's about synchronization or communication efficient algorithms for scalable machine learning. So I'll talk about 3 main components. One is quantization, reducing the amount of stuff we send. Quantization, sparsification, both of these reduce the amount of communication, but also efficient ways to implement this. And kind of, I'll briefly describe some of the challenges when having to deal with this. And as we'll see, this is not kind of a straightforward success story. We'll see that there's trade-offs between the amount of compression you get, like reduction in communication, versus the convergence of the algorithm, the sort of the quality of the models you converge to, versus the amount of parameterization, by which I mean like how many parameter values are you going to have to try until you obtain like a nicely converged model. Okay, and I'll also talk a bit about our work on implementing an open source framework which implements all of these techniques in a sort of single setup so that they can be used by like industrial partners and so on. So, and I'll kind of finish with an overview and maybe cover a couple of the things that I won't have time to go into in as much detail as I'd like. So the general setting for my talk, and this is kind of maybe for those of you who are more mathematically inclined and just want to think about the abstract problem that we're trying to solve, is basically as follows. So we have n nodes, n equals 2 in these examples so that it's just easier to draw. And they're connected, they basically act in a synchronous message passing topology, and we assume no faults in this talk. Okay, it's just about sort of you have a network works fine. So this is kind of the best case scenario. And what we do is we have a data set D and we split it among n components, right? So node PI is going to be a assigned data set partition DI. So basically in this n equals 2 case, we have two partitions, D1 and D2. And what's kind of special about these machine learning applications is that instead of a very simple problem or a seemingly simple problem like consensus, which is kind of where the objective is fairly easy to define, we have this kind of slightly more tenuous definition of what we want to sort of optimize for. And we have this, in order to sort of instantiate this, we have a loss function, which basically, given a model X and an example E, basically an image of a cat, is basically how good is the prediction of the model X, of the neural network X, on the example E, which is sort of the image of the cat. Okay, so basically this is just a way to quantify how good the model is on a specific sample. Okay, and obviously the thing that we would like to minimize or we would like to optimize for is basically the loss of the model over the data set we are going to talk about. And since we're splitting the data set, it makes sense to split also the loss functions into kind of F1, which is the loss of a model on the first data set partition, and F2, which is the loss of the model on the second data set partition. Okay, so basically, given this, what we want is we want to find a model which minimizes the sum of these two functions, right? So I mean, obviously, each node could optimize the loss with respect to their local data set. For this, they wouldn't need to communicate at all. But the whole idea is to take advantage of the entire data set. So we want to sort of minimize the sum, the sort of the joint optimization objective in this case. And the key quantity we care about is the amount of sort of communication or synchronization that has to go on between these two nodes in order for them to converge to a model X which minimizes. Okay, so this is the general kind of abstract problem we're trying to solve. How does stochastic gradient descent, the algorithm we're trying to analyze, solve this problem? Well, we have basically, we instantiate this as follows. We're going to instantiate a model or parameter X at each one of these nodes. So each one gets like a copy of X, which is kind of current at time t. So I'm going to call it xt. And then it's going to go over iterations until convergence, where it will select a sample uniformly at random from each one of their partitions. So one like sort of P1 does this, but also P2 does it in parallel. It computes the update, that is the gradient of xt at EI with respect to the loss function, which is kind of already encoded in the model. So, I mean, if you don't know what a gradient is or how to compute it, that's fine. You can just think of it kind of completely abstractly in terms of a set of updates, xt being kind of a vector of entries, and then the gradient being just updates to this vector entries, which hopefully give you a better prediction for the next step. And so each one of them computes this update relative to the sample that it has seen. And then what they do is that they average their updates in order to obtain like a total gradient, which is sort of puts together the two updates. And then they simply update their model, xt, by updating sort of with respect to this gradient times a learning rate, which is just a constant saying how aggressive you want to be in your updates at the step. Do you want to sort of go faster towards the sort of updates faster, or you want to be more conservative and put more weight onto the model you already have? Okay, so notice that if both nodes have the value of the average, if they average correctly, then both nodes will actually have will be able to obtain the same value at xt plus 1. So my point is, like, the invariant here is that if you start from the same xt, you're going to end up with, and you do the correct averaging, then you're going to end up at xt plus 1. Okay? So this might sound a bit convoluted, so I'll try to maybe sort of instantiate it, or like instantiate it through an example in a second. But notice, like, I just want to draw your attention to the amount of communication these nodes have to perform. So basically, assuming that my dimension is d, notice that they will need to send 32 times d bits per iteration. Okay? So in particular, if, for instance, if your model has about 60 million parameters, 32 times d bits, it essentially equates to about 250 megabytes that you would have to send from one node to the other in each iteration. And each iteration takes a couple of milliseconds, let's say, on a modern GPU. So basically, your network has to, in this case, your network has to take quite a bit of load very, very often. So it sort of makes sense to try to like study this and see whether it sort of reaches the bandwidth threshold of our network or not. Okay. So, all right. So let me try to give you an example. And the example I'm going to give you is what I call distributed mean estimation. So this is a very simple problem where, or a simple instantiation of this SGD sort of framework I gave you before, where all we care about, so we have like a bunch of vectors in D1 and D2, and we want to find the vector X, which minimizes the average distance between a random sample chosen from either D1 or D2 and the vector X, which is kind of our mean. So, I mean, this is just a convoluted way of saying we want to approximate, we have a bunch of vectors here and a bunch of vectors here, and we want to find a vector X, which is sort of approximates their mean as well as possible. Okay? So this is one instance of a loss function that we want to minimize. This is a particularly simple one, and it will be nice in that it will allow us to express what the gradients look like in a kind of intuitive way. So if we just plug in this loss function into SGD, what we'll get is that in each iteration t until convergence, each node I will select a sample EI uniformly at random from its local subset of the dataset. And then it computes the gradient of its estimate, which in this case will be simply the difference between the sample that it grabbed and its current estimate x underscore t. Sorry, this is just a bug in PowerPoint, which sort of sometimes moves the subscripts. But basically, the gradient here is really the difference between EI and the estimate xt. So for mean estimation, this makes perfect sense. Basically, what you're going to do is you're going to select a random sample, compare it to your mean estimate, and then you want to see how sort of close it is. And then what nodes do, so they each obtain sort of their sort of updates, and then they exchange them, they average them in order to obtain this sort of average estimate of the gradient of their update, and then they will update their estimates in order to obtain xt plus 1. Okay, so this is kind of the SGD algorithm instantiated onto this specific algorithm. So what's kind of interesting about SGD is that the algorithm kind of remains the same, whether we're optimizing something that's super complex like neural networks or solving classic regression. It's just the estimate, sort of the way this looks like, can be very complicated for neural nets, whereas for mean estimation or regression, this is fairly straightforward, right? In this case, the intuition is fairly simple. You just want to compare a random sample against your estimate and make sure that they're close to each other, right? So now a reasonable question is like, why are we doing this whole parallelization business anyway? And I'm going to try to explain this to you even at a more sort of abstract theoretical level, but the intuition is very simple. Like, notice that in one step, in terms of wall clock time, in this version of the algorithm, we're actually processing 2 random samples in one step, whereas in like a sequential execution, we would just be processing one random sample per step. So we're basically seeing more data per step. We're doubling the amount of data that we see per step, which should basically give us a better estimate of the mean of the true quantity we want to we want to estimate. So let me try to walk you through the actual sort of theory behind this. And this is kind of the last kind of theoretical slide you're going to see. So basically, so we want to minimize a general differentiable function f, and by the SGD iteration, which I sort of showed to you before. This is xt plus 1 equals xt minus learning rate times the sort of the stochastic gradient at xt. So we select a random sample and compute its gradient with respect to xt. And the key quantity we care about is basically how far this stochastic gradient, this gradient at the random sample, is from the true gradient, like the correct update with respect to the entire loss function. So how I select a random sample and compute its update, how far will this be from if I looked at all of the samples in my data set and computed the true sort of update that I would like to perform at this step, but I'm sort of limited in terms of the amount of data that I can see. So this is what I call this is called the variance bound for this step of the algorithm. And what we know from the theory, basically, you can go to books on optimization, is that if we have a function that's kind of nice and we start with a given distance from the optimum, then if we run SGD for t equals basically something that's proportional in the distance we started from and 1 over epsilon squared, sort of this is how close we want to get to the exact optimizer, times sigma square iterations, then we will get within some distance of the optimum for some definition of that. So the point, the one thing you have to be maybe a bit attentive to here is that the time we need to run in order to get like a good model is going to be proportional to this variance term. Okay. So why is it nice? Like, why is it sort of useful to do sort of distributed SGD? Because in this framework, if we're seeing p samples in one step, then our variance goes to sigma square over p. Okay, so basically our variance is divided by the number of nodes or the number of gradients we see, a number of updates we see in one step. So the more sort of samples we see, the lower the variance, and in particular, the faster we will converge. Because if we go back to this t term, then this becomes order r squared 2 sigma square over p. So basically, we just divided our sort of time to completion in terms of wall clock time by p. Okay, so what we are doing here is we're able to process, in theory, more, or like we're processing p times more samples per step, more examples per step. And this is supposed to give us a benefit in terms of wall clock time. Okay, so this sounds like very promising. Why isn't the story done here? Because the trade-off here is because we have lower variance, so we're seeing more samples, but we have to pay the cost of averaging. And averaging in a system where like you're averaging over things that are, I don't know, 200 megabytes to 1 gigabyte in size every couple of milliseconds, that's expensive. So that's what we saw in the couple of examples I gave you before, right? So the trade-off is between the improved convergence of the algorithm and the additional cost of averaging. Okay, so today's talk is going to be about how to sort of improve and move past these limitations. Okay, so I'll start by sort of the first method, the kind of one first way historically to go beyond this limitation, which I call quantization or gradient quantization. So the idea here is very simple. Have a vector, which is the vector of updates, which has many colors. These are kind of the sort of the exact values of the numbers in that update vector. Okay. The one reasonable question is like, do we actually need these updates to be very precise, or could we deal with basically just reducing their like their granularity to a very fixed set of levels? Here, like it's binary, it's either black or white. So do we need to send all of these different colors, or would SGD kind of be enough with a very coarse-grained quantization of the colors, would it actually be able to converge to the same thing? So as we'll see, this is possible, but it has its own pitfalls. Okay. So historically, the first paper to look at this in the context of SGD is a paper which proposes an algorithm called one-bit SGD, and which came out of Microsoft about 6 years ago. So basically, how does this work? Well, how it works is basically by, imagine we have a gradient vector, which is just a set of real values. In my case, this gradient vector has just 5 values, okay? And then what it does is basically it reduces these values to their signs, okay? Where so 0.1 goes to plus, minus 0.3 goes to minus, and so on. So you just preserve the sign bit. And then it computes the average over the positive values and the average over negative values, which in this case conveniently happen to be the same. And so more precisely, if we had a vector v that we're playing with, basically the ith entry would be replaced, if it's positive, with the average over positives, and if it's negative, then the average over negative, okay? So basically we go over the vector, and in some sense we make it uniform by removing everything but the signs. But then we want to keep some notion of scale, which is why we have like the average plus and average minus. This is just to preserve scale. Okay, and then crucially, there's going to be obviously a large quantization error, and this is accumulated locally and applied to the next update. So what does this mean in terms of the sort of compression that we get? So we had a huge vector of floating point values, right? Like d of these, 32 times d in total. And then we reduce this to 2 floats, one for the positive values and one for the negative values, and then d bits, right? Just the signs, okay? So our compression rate seems to be pretty good. This is 32x, almost 32x compression, just because we eliminated the exact values, and we replaced them with signs plus some scaling factors which are negligible, okay? So this looks like it pretty much solved the problem for all but the very sort of bandwidth constrained cases. However, this does not always converge, and this is something that they explain and sort of they try to mitigate in their paper. However, as we also saw, like when trying to reproduce this, then this is not a very general solution. You have to be very careful with how you sort of phrase it in order for it to work out. So basically, we looked into first proving one-bit SGD correct, but then we found that this is actually very non-trivial. And we were able to find a variant of it, which turns out to be sort of easier to prove stuff about, but also works better in practice. So this is what we call QSGD, and it was a paper which appeared in Europe a couple of years ago. So basically, we start from the same vector. And now what we first do is we normalize it. So basically, we compute a number which is called the 2 norm of the vector, which is basically going to be larger than any specific absolute value inside the vector. So if you divide by this number, you're going to obtain numbers between -1 and 1. Okay, and then we map these numbers onto a scale of some number of fixed values. Okay, so in particular here, imagine that we're going to use 4 quantization levels. So we're going to assume that all of the values are positive just to make things a bit easier. And then we're going to map them from 0 to 1. All of these values can be mapped from 0 to 1, and we have a total of 4 quantization levels: 0, 0.33, 0.66, and 1. So these are uniformly placed. Okay. So notice that these sort of entries, these quantization values can be just described as integer values, right? So imagine that the quantity, like the entry that I want to quantize, has value 0.4, which places it in here, right? In sort of in between the interval 0.33 to 0.66. So now a reasonable question is, how do I don't want to send this value in kind of plain text. I want to sort of compress it somehow. I'm going to map it to one of these 2 levels. I'm going to do this in a randomized way. So I'm going to flip a coin, and with probability proportional to this distance I'm going to map it here, and with probability proportional to this distance, I'm going to map it onto level 1. I'm going to replace it with 0.33. Okay, so basically, I'm going to map it to one of these two values in a randomized way. So what do I actually get in terms of what my vector looks like? What's the realization of this quantization technique? So basically, I started with this floating point vector, and I ended up with a bunch of integers, which is where these values landed, plus their sign. Okay, so how much compression do I get? Well, it really depends on the amount of, on the number of quantization sort of levels that I want to implement, and basically on the result of these random coin flips. But basically, what I would get in a rough fashion is basically 32 times d, which is what I had before, which gets mapped onto one float for the scaling factor, this 2 norm, and then d plus d times log s. So d is for the number of sign bits. I need to keep one sign bit for each entry. And then d times log s, like for each such entry, I will need to sort of encode it into log s, which is how much I need, how many bits I need to encode the number of like the level index at which this component landed. Okay, so basically my compression ratio is 32 over log s plus 1. So notice that this will be sort of similar to that of 1-bit SGD if I only use two quantization levels, but then it will be worse if I use sort of more. So now the question is, like, why would I use more? And this is what sort of the QSGD properties tell us. So basically, the first thing that's kind of nice is that this quantizer is unbiased, by which I mean, like in expectation, the quantized value equals the actual value that you had. This is the main reason why we do this rounding in a probabilistic fashion. And this is important from the theoretical level because it ensures convergence, if you remember the discussion we had at the beginning. So you needed the gradient estimator to be unbiased in order for SGD to work. Now, the other thing which is kind of nice here is that you get some guarantee on sparsity. So the expected number of non-zeros in the quantized vector is going to be at most s squared, the number of levels you use squared, plus square root of the dimension of the vector. So basically, this says that if you use very few levels, you're actually going to have very few entries, a relatively small number of non-zero entries. And then in terms of the variance blow up, like how much variance does this add to the whole SGD process and how much convergence are we actually going to lose? There's a blow up of 1 plus square root of d over s. So notice that this means that if I only have a constant number of quantization levels, so if s is 2 here, then my blow up is considerable. But if s is in the order of square root d, then my blow up is only a constant. So basically, if we have a non-trivial number of levels here, then this will ensure fast conversion. Okay, so in particular, if this is 2 if s is in the order of square root of the dimension. So if you have many, many levels, then we don't have practically any loss in terms of conversion. Okay, so notice here the trade-off between the amount of sparsity that I get. So if I would like to have very few non-zero values here, versus the loss in convergence due to the additional variance. Okay, so what does this mean? So kind of informally, what we showed in the QHDD paper is that there exists a setting of parameters for this whole scheme for which you can converge at most 2x slower than the full precision vanishing line, but also send 10 times less bits per iteration in one such iteration. Okay, so I'm gonna skip the proof sketch. I can come back to it in the Q&A session if you want. But the other thing I want to mention here is that there's no way to do significantly better than this. There are theoretical results showing that you cannot go past this kind of constant trade-off between the amount of variance that you induce and the number of bits that you need to send per iteration. There's just no way to do significantly better than this in the average case, in the worst case. And there's been a lot of follow-up work on this result, and there's some which actually slightly improves these guarantees in certain settings. Okay, so let's take a bit of a break from the math and ask a very simple question. Does this work in real life sort of systems? Okay. So for this, we're gonna look at some experiments we did for the original QHDD paper, and actually as a follow-up to it. And I'm gonna look at training a neural network on an Amazon VM with multiple GPUs. And we're gonna first look at a very classical model, which is called AlexNet, has about 60 million parameters, trained on the ImageNet dataset on 2 GPUs. And we're gonna compare the full precision version, which sends 32-bit values, with a version which does QHDD quantization with 4 bits per level. Okay, so S equals 16 here, and we're just going to run it without doing any additional tuning in terms of the learning rate or something to fit the fact that we're doing quantization. Okay, so all right, so it seems like this is slightly buggy, but I think we can work with it. So basically, per iteration, this takes about, like, the full version of this takes about, full precision version takes about 1.2 hours per iteration per pass over the data set, and you have to do about 100 passes in order to converge. And 60% of this missing part here is the computation part, and then about 40% of the time is spent communicating, right? So this is the overhead. And notice that most of this is actually sort of bandwidth bound. So most of this is because we have to send 60 million parameters every couple of, like any 10 to 100 milliseconds. So then what we do is we're able to reduce this bandwidth usage by about 8x because we go from 32 bits to 4 bits per entry, which reduces the weight of this from 40% to about 5%. So then, and from 60 to 40 sort of compute to communication, we go to 95% to 5% in terms of sort of ratio between communication and computation. So this results in a speed up of almost 2x, a bit less than 2x in terms on just 2 GPUs. Okay, we'll see some experiments on larger number of GPUs soon. Another very important question here is, what is this going to behave as when you sort of when you actually train the model? I mean, are you actually going to get the same accuracy? So this is the curve which describes how the accuracy of the model evolves as you increase the number of passes through the dataset. So an epoch is just a complete pass of a dataset. So we have basically, like, the thing I want to sort of draw your attention to is, like, you can't really see much of a difference between the sort of basic HDD run, which is in red, and then the 4-bit or the 8-bit runs, which are in blue. So these are pretty much the same in terms of accuracy. What's slightly surprising here is that the 8-bit QHD variant, so the quantized gradient variant, turns out to be slightly more accurate than the baseline, even though this is an effect which we can't exactly explain. So at least in one specific instance, this method seems to work, and it seems to perform better than the baseline. So now we did a lot more experiments to study this. So we looked at basically, so this is kind of the study on AlexNet on increasing number of GPUs, where we get up to a 2.5x speed up versus the full precision baseline. This is at 16 GPUs. And then we also have, like, on VGG19, which is a larger and more computationally intensive network, we get a speed up of about 3.5x, so which is again fairly significant. And then for ResNet 152, which is the original network I showed you before, there's like 1.x speed up. And then on inception, there's also 1.3x, so about a 30% improvement in end-to-end accuracy. For some reason, these graphs are not exactly, there's part of them missing, so maybe people can look at the PDF version of this after the talk. The other thing I wanted to mention here in order to draw a conclusion is that notice that some these speedups are sort of proportional to how they're kind of model specific, right? So they're actually proportional to the compute versus communication ratio of the of the models themselves. So notice my point is that you can't expect like a blanket increase in throughput of 2x for using this method. It really depends. It's kind of Amdahl's law. It really depends on how much time, right, proportionally, you actually spend on communication versus computation. Okay. So, all right. So we have some additional experiments on speech recognition, which I'm going to, because we have more interesting stuff ahead. So to summarize, we looked at quantization as a method of reducing the communication overhead of these models. And there's been quite a bit of follow-up work to do this compression. I think there are upwards of like 200 papers published on this in the past few years. The amount of compression you can do is usually less than 32x, since it's just bit width reduction for one single entry. So you can't go beyond like below 1 bit per entry on average, even though there are more recent methods which try to do this. So unfortunately, it doesn't seem like you can do much better than this without incurring a large amount of variance. So basically your maximum compression is about 32x. If that's enough for you, then good. If it's not enough, then you need to look at some more fine-grained methods. Does it guarantee convergence or accuracy? Does it actually guarantee that you're going to get sort of the same result out as if you didn't use this method? Yes. So it turns out you can prove convergence, even though sometimes you have to assume some very strong assumptions. So what we were able to show by some somewhat extensive testing, like upwards of 30,000 node hours of compute in total, is basically that the QHDD compression can preserve accuracy for all networks that we sort of tried across a wide span of networks. Do you need additional parameter tuning? It sort of depends. So QHDD, we are fairly confident it does not, but some of the other methods which can give you higher, can get you closer to 32x in terms of speed up, they might need this. Okay. So, all right. So where are we now in terms of the plan for the talk? So we looked at communication efficient algorithms, and I looked at quantization first. We sort of looked at its pros and cons. And now another method which has been proposed is basically to simply remove entries. So basically we have this vector, which is sort of the first vector as we had before. And what we can do is you can completely remove some of the entries. You can try to basically identify the entries which are kind of important for the algorithm and just send those as opposed to sending all, right? So this is what I'll briefly look into now. In this method, it's called structured sparsification. Okay, so basically structured sparsification does the following. Like imagine like one instance of this is basically the following. So imagine I fix a parameter k, which is however many entries I want to send per iteration. And I'm only going to send the top k entries in terms of absolute value. I mean, basically thinking that the max, like what the best thing I can do is actually sort of sending the top k like the magnitude means importance here. So I will just do this, do things this way and accumulate the unsent values locally. So algorithmically, what this looks like, if we take our previous vector here into consideration is, and I want to only send the top two, I will sort these values by their sort of modulus, and then I'm going to select these two. I'm going to send them. Okay, so I'm going to send k times 32 times log d bits. 32 comes before because I send this kind of clear text value. K comes from the number of values I send, and log d comes because I have to send their indices in this vector of the entries. And then I'm going to compute the error locally. There's zero error for the values I send, but there's non-trivial error for the values I did not send. And then I'm going to add it to the next gradient. So I'm just going to push it into the next gradient. Okay. So notice that this actually breaks our previous analysis for QHDD because the gradient estimator is not unbiased anymore. So in expectation, your error is not zero. Your error is non-trivial. Okay. So what does this give us in terms of compression? Well, it gives us a compression factor of dimension over k times log d dimension. So basically, if I take k to be very, very small, this can be potentially huge. I mean, if in theory I took k to be 1, then my compression factor is like d over log d. And if D is 1,000,000, then this is practically unbounded, right? However, and this would also mean that I would only send one entry per per vector, which is probably not a good idea. So this actually guarantee convergence. Kind of interestingly for this method, kind of experimental evidence that it works well came way before, or significantly before its theoretical understanding. So there was a paper showing very impressive experimental results at basically up to 400x compression with no accuracy loss via extremely careful parameter tuning. And then we were able to kind of follow up on it with a paper showing that you can actually guarantee convergence for this method. Okay. Do we need additional hyperparameter tuning? Yes. In general, yes. But we also were able to find in a recent paper some fairly generic setting of parameters under which you don't need to change the learning rate or momentum parameters to make this work. Okay. So in particular, we were recently able to show that basically formally that this method converges. So under some analytical assumptions, giving any smooth function, there exists some learning rate sequence such that your gradient converges to 0. So basically you obtain like a sort of optimum of this loss function. So what this says morally is that this will eventually converge to a local minimum of f, which is kind of the best thing that you can hope for with SGD. And then that is convergence rate depends linearly on however many entries you send. So basically, the more entries you send, the kind of faster you are going to be in terms of convergence. Okay, so so this is kind of the best you can hope for in terms of theoretical understanding, and this actually sort of suggests that this method is kind of well connected to an asynchronous variant of SGD, which has been studied in the shared memory world. Okay, and the key parameter we care about is how much of the gradient norm, how much of its sort of magnitude in some sense is transferred in the top K, basically. And one thing that I wanted to mention, since people might care about this in the concurrent world, is that this would work well even if you did things in a shared memory setting. So basically, this method allows you to practically write less. You write to less entries, so there's less potential for contention. So this could be a strategy. This kind of sparsification strategy can be a strategy that would work well in a concurrent kind of shared memory setting as well. Okay, so let's maybe take again a step back from the sort of technical discussion and summarize what we saw so far. So we care about algorithmic methods for scalable distributed machine learning, and we looked at quantization and sparsification. And then this can kind of provide order of magnitude communication reduction. So we saw that the sort of like what you can reasonably get with like quantization methods, with the first type of methods, is about 10x or 8 to 10x. Whereas in the case of sparsification, you can expect stuff that's like up to 100x, right? With reasonable convergence. But however, one thing that we noticed once we played with this a bit more is that there's very little in terms of software support for implementing these methods. So if you're familiar with stuff like MPI or NVIDIA NCCL, these are basically communication libraries which allow you to instantiate a set of processes and send messages between them. However, those messages are kind of inherently assumed to be 32-bit, and they're assumed to be that memory is assumed to be dense and expressed in 32-bit values. So you would have to hack MPI in some sense in order to support these things. So one more generic question was sort of from the research side was like, can you actually design a piece of software like a variant of MPI which would like natively support sparse or quantized types? And this is what we sort of took a first step towards in ScaleML, which is a scalable communication framework for designed for machine learning. This appeared in supercomputing late last year. So basically, the main idea behind this is that you want to build a communication framework which sort of has MPI like semantics, so you can do all reduce, scatter, all gather, and so on. However, you should have native support for quantization and sparsity. And there are a couple of things kind of that are interesting here. In particular, efficient sparsity support turns out to be non-trivial because these nodes, I mean, each one comes with some kind of sparse vector as its input, and they want to average these sparse vectors. But notice that like the sparsity patterns are not the same. They can be very different. In particular, they could be random every node. So now the question is, how, I mean, notice you're in a setting where your inputs are sparse, but your outputs to this sum might be dense. So then you would actually, you have to study kind of the method carefully in order to obtain something that's kind of non-trivial in terms of like algorithmically in terms of efficient support. So in the dense case, if we do all reduce, so each one of these nodes has like a dense vector to sum, we know exactly what the size of the result is going to be. It's going to be exactly the same dimension. However, if these nodes have like potentially overlapping inputs, and notice that their their outputs might have very different density patterns. So our method has to adapt. So basically, there are kind of two main questions we had to sort of answer in the implementation, or like consider during in the implementation. One is, can the data become dense during aggregation? So depending on this, depending on whether the summed vectors sort of become dense at some point, we can actually switch to a dense quantized data representation dynamically. So basically, you swap from a sparse vector representation to a dense one, but then you quantize it in the same step. And then the second thing is like is actually the system latency dominated or bandwidth dominated. So if the system is latency dominated, then you might want to use a completely different reduction pattern, like communication pattern between the nodes when aggregating. So basically, this is an instance of an optimal communication structure for the latency dominated case, which looks a bit like a binary tree. And then with respect to the like in the bandwidth dominated case, what you want to do is more of a sort of flat structure where you just reduce in a more all-to-all sparse algebraic pattern. Okay, so what does this actually get us in practice? That's always kind of a good question to come back to. So basically, what we get on CSCS distinct is basically that on 8 nodes with sparsification up to less than 1% sort of dense vector. So we throw away all but 0.5% of the entries in the vector. We sort of store them locally and store them as error. Plus, on top of that, we do 8-bit quantization. We're able to get a 2.6x speed up in end-to-end convergence, like time to convergence for the training of this speech. And then on an Amazon cluster on exactly the same setup, we get about a 7x speed up in terms of end-to-end conversion. So the difference here, this is exactly the same setup, it's the same software, it's just that the network on Pisdaint is much faster than the one you would get on EC2, which is what kind of limits the speedups you can show. So we can also observe that this works in a variety of other models and settings. However, I mean, this is still kind of an academic environment you might not be completely convinced about. So does it actually work in the real world? And to answer this question, we partnered with some people from Microsoft. And Microsoft has one of the most advanced groups in automatic speech recognition. One of the things that they use this for is basically to train their sort of personal assistants. So for this, they have at least 30,000 hours. So basically, they train on at least 30,000 hours of transcribed speech. So this is something that's an order of magnitude above like the academic data that you would see in this setting. So we use a similar setup as for the academic example I gave you before. So we throw away, we sparsify the vector to less than 0.5% of its density, and we use 8-bit quantization. And for this, what we, like in this context, what we start from in terms of their sort of baseline is, like for them, it took about 14 days to train their model end-to-end on 16 GPUs with their very fine-tuned baseline. And this was basically the maximum number of nodes at which they were actually able to make a converge. If they had more GPUs, but they weren't able to use them because the model would basically diverge. So we were able to reduce this with sort of compression. We were able to first use more GPUs. So we were able to go to up to 128 GPUs, but we were actually able to reduce this to 1.7 days. So that's a fairly significant improvement of about 7x, I guess. So in terms of scalability, in terms of like versus how close is this to the ideal scalability, as you can see, this is not ideal, but it's still fairly okay. So it doesn't, in particular, it doesn't stop at 16, which was kind of the best thing known, at least on their setup before we started. So we were pretty happy about these results because they actually do show that you can get a non-trivial speed up in this context. Okay, so maybe the like qualified conclusion here is that seems like we can actually leverage this in the real world. Okay, so in summary, I mean, I'm sort of winding down my discussion so far. So we talked about algorithmic methods for scalable machine learning. We discussed quantization, sparsification, but also kind of efficient ways to implement this and deploy it in the real world. Hopefully it was clear that I'm not proposing these as a generic, like total solution to all your machine learning worries. So in particular, there are these trade-offs between the compression you get, the speed that will actually generate versus the amount of parameterization. And then the thing I'd like to sort of end on, and I'm happy to discuss more in the Q&A, is basically that this is a wide open area. So there's a lot of interesting stuff to do for someone who's interested in distributed or concurrent computing. So I'm happy to sort of answer questions. Well, the thing I wanted to sort of end on is basically like there's been a ton of work, which is very interesting, but I couldn't cover it today. In particular, there's a lot of work on concurrent computing, so basically asynchronous machine learning. Basically, how does all of this map onto the shared memory world? I mean, we know a bit about that. We worked on it as well. However, just in terms of like talk flow and so on, I just had to make a conscious decision to avoid that or shorten that. And then there's a lot of work on dealing with faults in this setting, crash faults, but also Byzantine faults. So then, again, like unfortunately I couldn't cover that, but I'm really happy to cover these in the Q&A. So I think with that, I'll stop here, and I'm happy to sort of take questions.
Thank you, Dan, for an excellent talk. Actually, it's one of my favorite areas, distributed machine learning, and I don't think it's a closed question. Of course, there are a lot of things to do there for sure. And maybe I'll start with the first question. You've been talking about a framework, Scalable. I'll try to Google it, but I felt, is it open right now, or is it kind of a future work you want to open? What can we do to try the framework?
So, I mean, if you want to try there are parts of it which are available. There's like we have a couple of implementations for QSGD specifically, which are sort of already available and can be accessed. They're tied to CNTK, which is kind of Microsoft's deep learning framework. There's also, if you want to try out the code which specifically gave us the experiments for I showed right at the end. That's also available. However, like what we're actually working on right now is basically putting all of those together in a framework which would support both TensorFlow and PyTorch and maybe potentially MXNet as well. So this is still an ongoing effort, and we're planning to have something released by I guess by September or like later in the year.
Oh, that sounds great. And from the user perspective, how it will look like. So I'm building a model in CNTK or PyTorch, and it's transparently converted to distributed mode, or should I do some extensive preparation? How it will look like?
So, yeah, that's a very good point. So the way we envision this to work, and the way it actually does work on sort of our private framework is, so there's like PyTorch and TensorFlow as well does give you some kind of default options for how to distribute your computation. That can be, in PyTorch, it's called either data parallel or distributed data parallel. I mean, they're also kind of more funky versions, but those are kind of the two ones that people use. And what exists already, and this is very nice work by some people who were formerly at Uber, this framework called Horovod, which is kind of like some sense a base framework which makes the interface between the Python code, which is done like just used for training, and the sort of C code on which sort of MPI and so on work. And what we do is we sort of embed inside this interface, and it's there that we sort of implement the compression algorithm. So the idea would be for this to be sort of transparent to the user. So you can use your standard data parallel or distributed data parallel version of the PyTorch code and just run over Horovod in order to get like proper compression in.
Oh, that sounds great. I think we will be very glad to try. So looking forward. We have 15 seconds, so I propose we'll switch to the discussion zone and continue discussion there. And thank you very much. It was an excellent talk.
All right, thank you for the invitation again. Looking forward to the discussion.
Yes.
Dan, thank you very much for your talk. And there is a small last question probably from my side in this broadcast is, there is a marker board behind you. And what is painted on it?
Well, I mean, which board exactly? Which color exactly? I mean, here you have some binary trees which are used as worst case instances for belief propagation, like concurrent belief propagation. And there I think you have some instantiations of like sparse reductions or something like that. So
okay,
that's the quick version. And then the thing on the last one is super secret, so I would.
Okay, okay. So guys, you can see some super secret. But don't worry, we have a not very good resolution from your camera, so I'm not sure this is. We can share this top secret to our audience, but maybe there are some, hackers who can,
Yeah, if people are able to solve that last one, they should just email me directly.
Yeah, some probably they can just zoom the corresponding part of the frame and restore the original picture using some machine learning or distribution machine learning systems. Anyway, thank you very much, Dan, for your talk, and thank you very much, Dmitry, for your help with this talk. And again, as Dan and Dmitry already mentioned, just below the player, please press Zoom button and join Dan and Dmitry in the discussion zone right now. Thank you very much for the broadcast and for the talk.
Thank you.
Yes.